So I'm thinking that today we will just finish up 8.1. So if you have any questions while we work on some example problems and we go through the lecture, just feel free to ask those questions. Keep them relevant to the lecture discussion though. And then if you have something that doesn't relate immediately to what we're covering in class, just hang on to that and we can talk about it after the lecture is done. Okay. So last time we talked about different sets of numbers. We talked about the natural numbers, which was the set of numbers that was given by this symbol n, and the set of numbers here. Let me go ahead and there we go. The natural numbers started with 1, 2, 3, 4, and so on. This is just a recap, so you don't necessarily have to write this part down if you have it already. Then we said, okay, if we're going to take a step further in our number system and add a level of complication maybe to it, we're going to call the whole numbers all of the natural numbers, but now we're going to include 0 in that category. So 0, 1, 2, 3, 4, and so on. And those will all be called whole numbers. So you might notice that if I ask you to identify which of these numbers in this set is a whole number, well, that's all of them. But if I ask you which of the set is a natural number, well, then you would say that, well, only these are natural numbers. Okay. Then we took a step up from there and we discussed the integers, which again, sort of in our common everyday language, we might say that negative numbers like -1, -2 are whole numbers. But by this definition, by this convention that we're using, we're not going to consider those whole numbers, not the negatives. The negatives are going to be considered integers. So if they look like they're whole numbers, but they're negative, we're not going to call them whole numbers. So 0, 1, 2, 3, and so on are all integers. But the integers also contain the opposite of the whole number. So -1, -2, -3, and so on. So we can say within the integers, we have contained all of the whole numbers. We also have contained all of the natural numbers. And then we have maybe another categorization here, which we might just call the negative integers. And we had to introduce the integers before we could build up to the rational numbers. Now, the rational numbers, I don't think I gave you a symbol for that last time, but in typical mathematical fashion, you get a symbol that looks like a Q, like a bold-faced Q, and that is the set of all the rational numbers. Rational numbers could be negative numbers like -3, -2, and so on. 0 is considered a rational number. 1, 2, 3, and so on are also considered rational numbers. But here in the rational numbers, we also have things like fractions. So things that can be written in the form of, let's say 5/3 would be an example. And we said that they take the form n/d, where n and d can be any integer, but the denominator cannot be 0. Okay, so this might look a lot very confusing or sort of crazy, but all I'm saying here is that inside of the rational numbers, you have all of the natural numbers. All of the negative integers are rational. All of the whole numbers are rational. And then everything else that clearly looks like a fraction, like 5/3 over here, something that can be written as one number over another number, those are rational. Okay. Anything that can't be written as a fraction. Well, let me before I go on to that, we sort of looked at rational numbers and their decimal representations last time. So we looked at 1/2, and we did long division to determine that, we could look at 1 divided by 2. We could do the long division, and then we'll find that 2 goes into 10 5 times, so we get 0.5. Okay. That if we're looking at the decimal representation of a fraction, and if that decimal representation terminates or has a definite ending, this is just 0.5 and there's no trailing decimal values, that if it has a terminating decimal, then that's how we can tell that that number is rational, just by looking at the decimal representation. Additionally, we might look at a number like 1/3, and we could do long division here as well, where we take 1 and divide that by 3. But we're going to run into the same issue here. 3 can't go into 1, so we put a 0 up there. 3 goes into 10 3 times as 9, but we have a remainder of 1. Go ahead and get rid of this really quickly. There we go. So we drop a 0, and then we're in the same situation where now we have 3 going into 10 3 times as a 9. We subtract that, we'll get a remainder of 1. So we can see that pretty clearly 0.333 repeating is going to be the decimal representation of that fraction. So if we're just looking at the decimal representation, and if it's non-terminating and has a repeating pattern, that's another way that we can identify it as a rational number. Okay. Does anybody have any questions so far?
Unit post is right in the Canvas, correct?
Yes. Okay. Well, there's another category of numbers called the irrational numbers. And by definition, these are numbers that can't be written as a fraction. So cannot be written or expressed as a fraction. These are things like pi, which you might know the value of pi. Does anybody happen to know the value of pi?
3.14.
3.14, 3.14. And that's a pretty close approximation, right? If I were to grab my calculator here and we were to compute the value of pi, 3.14159264. So really there's more decimal values behind the 14. So 3.14159264. And if I had a supercomputer, I would actually be able to calculate more and more of these trailing decimals. In fact, the decimal values continue forever, and they don't have a repeating pattern. So that's one way that if you're looking at a decimal number, you can identify that it is not rational or that it is an irrational number because it is non-terminating, and there is no repeating pattern in the decimal values. Okay. There are other fancy mathematical constants or terms that come up in higher mathematics. Like there's an irrational number that's called Euler's number, which is represented by the letter E. That value is approximately 2.718281828, and that sort of looks like it has a repeating pattern, especially with the 8s. But this is another example of an irrational number. Another one might be the square root of 2, which I think we talked about last time. The square root of 2 is about 1.414213562. Not super important that you write these decimal expressions down, but what it is important to get down is that to identify an irrational number, a lot of the times we have to take that value, look at its decimal expression, and if it is non-terminating and has no repeating pattern, that's how we're going to be able to distinguish it from the rational numbers. Okay. And I will say this, that things that have roots, this root symbol, so many numbers that are roots may be irrational. You'll have to check them in the calculator. Okay. So for instance, I know that the square root of 11, if I put that in, will give me this really ugly looking long decimal value. And if I look at the decimal values, 3, 1, 6, 6, 2, 4, 7, 9, they don't seem to have a repeating pattern. So I think I'm safe to say that that is irrational. But if I put another random number and took the square root of that, like 25, notice that the square root of 25 is just 5, according to my calculator. That is a terminating value. There's not a long list of decimal values. Since it's terminating, I know it's rational. Okay, so some of these roots may be rational. Some of them may be irrational. You'll have to check those in the calculator. Okay, but why am I telling you about these categories? Well, primarily it's because you're going to run into problems in the homework that ask you to identify, given this list or this set of numbers, which ones are the whole numbers? Which ones are considered integers? Which ones are considered rational? And you'll have to be able to classify them yourself. Okay. And knowing the classification of the numbers is just sort of helpful for solving other kinds of problems later on. But in general, this is how the number system works. We have something called the real number system. And like I mentioned last time in class, there is a larger number system called the complex or the imaginary number system. And that is useful in higher mathematics and engineering classes. But for our purposes, all of the numbers that we're going to work with in this course are considered real numbers. The real numbers are broken up into two categories. So I'm going to make a big bubble here. The rational numbers and then the irrational numbers. Now, like I mentioned before, your rational numbers contain all of the numbers that can be written as fractions. So 1/2 is a rational number. -5/7 is rational. 10/34 is rational. Okay. The irrational numbers are going to be the things that have weird decimal representations, like what I've shown above. Within the rational numbers, that is, inside the rational numbers, we also have the integers. Because if you think about a given integer, let's say the number 3, if I wanted to, I could also express the number 3 as 3/1, right? It can be written as a fraction, has the same value, So the number 3 is both an integer and it is rational. Okay. But the integers also contain your negative number. So let's put like negative 13 here. Within the integers, we have the whole numbers, where 3 is considered a whole number. Remember, 0 is considered a whole number. And basically, the whole numbers refer to the positive integers. So 1 and 2 go in here as well. But then we know that 1, 2, and 3, 4, 5, 6, and so on are also considered natural numbers. So this is basically how the number system is organized. The natural numbers belong to the whole numbers, but the whole numbers has a little bit extra. Then the whole numbers are all integers, but the integers also contain the opposites of the whole numbers, that is, all of the negative integers. All of the integers are rational numbers because they could be written as fractions, in the same way that 3 could be written as 3/1. And then all of the rational numbers and the irrational numbers combined make up the real numbers. Okay. Now that being said, we're going to have to keep this diagram in mind as we move on to this next example question, to sort of test our skills of how well do we understand how these numbers are organized. Okay. So let me write down a question for you guys. Practice. List the numbers in the set S is equal to -5, -3/4, 0, the square root of 2, and 17. That are A, whole numbers. Okay, first question. You're given a list of numbers here in this set: -5, -3/4, 0, the square root of 2, and 17. Which of these are considered whole numbers?
0 and 17.
Yeah, 0 and 17. Does anybody have any questions about that one? Which ones are considered integers? So among this list, which of these values is integers? Any question or any questions, comments, or concerns?
It's -5.
-5 is definitely an integer for sure, right? Because the negative integers, the negative, what look like whole numbers but have a negative sign, right? Those are considered integers for sure. Are there any other integers here?
0 and 17.
Yeah, there we go. 0 and 17 are considered integers. Remember, we have to be thinking about this diagram here. And the integers contain all the whole numbers. So if we see whole numbers here, like 0 and 17, well, those are also integers. Okay. What about rational numbers? Which of these numbers is rational? List all of them that are rational.
-3/4.
That's definitely a rational number for sure.
All of them are rational, except for the square root.
Yeah, that's perfect. So all of these numbers are rational numbers. -5, -3/4, 0, and 17. The square root of 2 is the only one that is an irrational number. So if I asked you to list all the irrationals, well, that would just be the square root of 2. And then if I asked you to list all of the real numbers, which ones would be included?
All of them?
Yeah, all of these numbers are real numbers. Might seem like a silly question to go through this exercise, but again, it's something that you're going to experience, you're going to see in the homework in Hawks. So I just want to make sure that you're prepared to answer a question like this to know what it's asking. Like I said, there are numbers outside of the real number system that are called imaginary or complex numbers, but we don't really get into complex numbers in this class. If you make it into college algebra, you will be exposed to those imaginary numbers and complex numbers later, but we're not going to really worry about them. We're not really going to see them in this class. Do you guys want to do another problem that's like this?
I have a question.
Yeah,
Versus list of the numbers in sets, is that a letter S or a 5?
this is the letter S.
Okay.
Yeah, I'll try to be a little bit clearer when I have an S or a 5. Usually for things like that, I will use a cursive letter. So I'll try to be a little bit clearer when I'm writing these things. Okay, well, some of the other problems that you might run into in Hawks are things that ask you to graph the set of numbers. So let's do some more practice. Graph the set of numbers. So we're going to give you a set like -3/4, 0, 1, 1.5, and 3. And you'll be given a number line in Hawks, and the number line will already be set up with tick marks, so you don't have to draw it by hand. It might have 1, 1.5, 2, 2.5, 3, 3.5, and so on. It might have 0.5 here, 0, -0.5, -1. Okay. And in order to graph on the Hawks system, what you will have to do is click on the location of this number line where each of these values belongs. Okay. So if I asked you, let's find the location of -3/4, does anybody know how I would go about finding where this should be located on the number line? Any ideas? Well, maybe let's skip that one for now. If I was trying to find the location of 0, is that one pretty obvious to you guys? We would just find the location of 0, and on Hawks, we would click right there and put a dot, right? And that's going to be graphing 0. Does that make sense? So for all of these for which we have a tick mark and they're clearly labeled, we can go over here and put a tick mark on 1 or a dot on 1. We've graphed the number 1. 1.5 is listed here, so we can go ahead and graph that one, and also 3. Okay, but we won't be able to submit our answer until we figure out how to graph -3/4. So if you recall from last class, if we needed to find the location of one of these numbers and it's a fraction, then we might need to convert 3/4 to a decimal. That might be a helpful strategy, right? And I know that I've forgotten the negative sign here, but this is just so I can get the decimal representation of the fraction part, right? We know that because it's negative, it'll be to the left of 0. But in order to convert this to a decimal, we need to do long division. So remember, cowboy sleeps inside and the horse sleeps outside. So we can go ahead and do this long division. So does somebody want to walk me through this long division? How many times does 4 go into 3?
None.
Yeah, 0 times. How many times does 4 go into 30?
Seven, so that equals 28.
Yeah, so 7 times 4 is 28, which means that when I subtract this, I should get 2. I can drop this 0, and then ask myself, how many times does 4 go into 20?
Five times.
5 times, right? 5 times 4 is 20. So I can subtract that and I'm done, right? Because I got a 0 here, there's no remainder. That means that if I'm really working with -3/4, -3/4 should be equal to -0.75. Does anybody have any questions about that? So if I have this decimal representation now, can somebody direct me to where this belongs on my number line? Where would I put this dot?
The 1 and the 0.5.
Between the 1 and the 0.5?
Yeah, or somewhere in between there.
So over here?
The negative.
The -1 and the -0.5, right?
Yes.
Yeah, right in the middle. So that would be where -3/4 goes. Right there. Does anybody have any questions about that placement? Let me put a dot there. There we go. And when you drag, basically when you click or drag one of these dots on the Hawks homework system, you should see a little number pop up here that tells you what location you're at. So you should be able to find that this is the location of -3/4. Any questions on that problem? Okay. So the next thing that we have to get into is a discussion of inequality symbols. We're still in 8.1, so no worries there. Have not moved on to another section. But the first thing that I want to talk to you guys about is equality. I've been using equality or equal signs throughout this lecture, and I just sort of assume that you know what we mean when we use the equal sign. Okay, but I want to be very clear about what the equal sign is. So given two numbers or two expressions, so let me put the expressions as letters or variables, A and B. If I wanted to compare them and say that the statement A equals B means that A and B have the same value. They might not look the same, but they are worth the same amount. You can think of it that way. And like I said, we've seen some expressions like this before, like when I said 1/2 is equal to 0.5, right? We can manipulate 1/2 or 1/2, throw that into our division algorithm, do the long division, get the decimal representation. And so those two things, even though they look different, have the same value. Okay. And those kinds of concepts come up time and time again in mathematics, where solving some problems requires you to convert from one representation to another so that you can solve the problem more easily. For instance, we should know that the number 2 is equal to the expression 1 plus 1. Or I could also say that the number 2 is equal to 2 times 1. Or I could say the number 2 is equal to 10 minus 8, right? And I can come up with a bunch of different expressions that mean the same thing. But fundamentally, the equal sign is saying that whatever you have on each side of that equal sign, they have the same value. Okay. And they have to have the same value in order for that statement to be true. Okay. So just you might not have thought about it explicitly what the equal sign means, but whenever you see something in math that has two expressions that are connected with an equal sign, it's just a statement that those two things have the same value. Okay. An inequality is an expression that two quantities or two things differ in value. But when things differ in value, we can talk about them in different ways. So you might see symbols like this. Let me go ahead and continue using A and B. A, and then we'll use this symbol. And this indicates to us that whatever the value of A is, it is less than B. Right? Like A could be my age and B could be the age of my older brother. And so if we were comparing our ages, well, I'm younger, so my age is less than his age, right? So we would use this symbol here. And in probably previous math classes in grade school, you might have heard that the alligator here eats the bigger value. Okay. So that's all we're going to say, that I'm introducing this symbol so that if we need to compare two values or evaluate a statement, whether it's true or not, then that is how we will read this symbol. A is less than B. Something is less than something else. Okay. We might also see an equality statement like, let me go ahead and switch this so I don't confuse anybody. B, I feel like I've already confused us. Go with B is greater than A. So if this symbol is sort of flipped around, then we read it differently. We'll say B is greater than A. And finally, the symbols less than or equal to and greater than or equal to indicate that it is possible that the quantities or the things that we're comparing have the same value. So again, this sort of looks like a combination between the less than sign and the equal sign because it has a little bar underneath it. So we call that the less than or equal to sign. Again, less than or equal to, because it's possible that the quantities could have the same value. It's possible that they're equal to each other. And then this symbol, which looks like a combination of the greater than symbol and the equal sign, indicates that something is greater than, or it's possible that the quantities have the same value, greater than or equal to. Does anybody have any question about those inequalities? Okay, let's try to interpret them with some practice problems. So I'm going to give you a list of statements, and I need you to determine if they are true or false. So determine if the statement is true or false. Okay, so I'm not going to read it to you because I feel like that would give it away. But is this a true statement?
Yes.
Yes.
How would you read this statement?
7 is less than 15.
Yeah, so you would read it as 7 is less than 15. And if you needed to verify that for yourself, you could plot 7 and 15 on a number line. You know that if 7 is here, then we should have 8, 9, 10, 11, 12, 13, 14, and then eventually we'll get to 15, right? And we can determine that 7 is lesser in value compared to 15 because numbers to the left of the two numbers that we're comparing, the one on the left has the smaller or the lesser value. So the left, I'm going to put numbers on the left have lesser value. We should sort of intuitively know that. But if we're not like intuitively aware, when we move to the left on the number line, we get smaller numbers. Like if I were to count down from 7, I would be at 6, which is smaller, 5, smaller still, and so on and so forth. Okay, so comparing them on the number line, the one on the left is smaller. So this is a true statement. Okay. 2. What about this one? Is this a true statement? Well, first off, how would you read this statement?
I'm going to use the restroom real quick.
Yeah. Anybody want to take a guess at reading this one?
3 is greater than -1.
3 is greater than -1. Is that a true statement?
Yes.
Yeah, that's true. Is everybody okay with why that's true? Is there anybody who's not okay with that? All right, well, remember that we could plot these numbers on a number line. We're comparing we're comparing 3 and -1. So if I put 0 here, just as a reference, I know that -1 belongs over here on the left side of 0. There's my -1. And I know that 3 would be 1, 2, 3 tick marks over here on the right side. So the numbers on the right have greater value. So this has to be a true statement. But let me give you something that might be a little bit more complicated. Okay. Can somebody tell me how I would read this statement?
-5 is greater than -125.
Yeah, that's how we would read it. -5 is greater than -125. Now, is that a true statement though?
Yes.
It is a true statement. Does anybody disagree? Okay, cool. Well, if nobody disagrees, then yeah, if we look at this on the number line, we're dealing with negative numbers, so I'm going to throw 0 all the way on the right. I know that -5 would be, I count 1, 2, 3, 4, 5. That would be my -5. -5 to the left of 0. But then -125 would be like way over here somewhere. So I'm just going to put a big tick mark and put -125. So we'd have to count many tick marks to get to -125. And again, even though this sort of looks like a larger number, and a lot of students have sometimes get confused by this, it looks like a larger number, but it's a smaller value. If you think about what you would rather have in your bank account, well, I would rather have positive money in my bank, first of all, but if I had to choose between one of these, I'd rather have a -5 because that's closer to me paying off my debt. That's closer to being to 0. In other words, if we just look at the number line, again, the numbers on the left are smaller or lesser in value. So this is a true statement, even though the number 5 looks bigger. I'm sorry, it looks smaller. Okay. All right, let me give you guys a couple more of these. Let's make it a little bit trickier. Let's compare the following. Is this a true statement? And I'll go ahead and read it because I think that we're getting good at reading this, but it's -1/2 is less than or equal to -1/4. Is that true?
No,
Is this one a little bit trickier?
it's not true.
It's not true. Okay. How did you figure that out?
Because 1/2, if we're talking about like money wise, it would
Yeah.
be like half of 1, but 1/4 would be number wise more, but if we're talking about negatives, less.
Well, I think you're thinking about like just the number 2 and the number 4, right? Like this one looks like it's bigger. But then like when you go into the negative, you're saying that you have to flip that.
I think if we put it into decimals, it'll be easier to like.
Yeah, that's exactly what I was hoping that somebody would throw out. I think that when we're dealing with fractions, it's hard to tell what the size of the number is. So what we should do is convert this problem to decimal. And so what we'll do in order to do that is like, if I had half of $1, what is that in terms of change in cents? Yeah, it's 50 cents. So it's 0.5, right? 0.5. And I still have my negative sign. So I have like -50 cents in the bank. And I'm trying to compare that to this thing, which is 1/4. Okay, so we're sort of holding the negative sign, but we want to figure out how do we get 1/4 in a decimal? Well, if you know that 1/4 is also called a quarter, like if I had a 1/4 cup, you would say a quarter cup. a quarter's value is 0.25. So now, just a quick trick, so that we can get those quickly into decimal form. The other way that you would go about doing this, which we've done previously, is you could take 1/2 and do the long division, 1 divided by 2. You'll have to drop a 0, but what you will end up getting is 0.5. The same thing with 1/4. If we do 1 divided by 4, we'll go ahead and run through this long division. We need 2 decimals here. 4 goes into 1, 0 times. 4 goes into 10, 2 times as 8. So 10 minus 8 is 2. Drop our 0. Goes into 25 times as 20. And so we finish up there. So that's the way we can get their decimal representation. Now, you could look at these two numbers and say, okay, which one is smaller? Is negative 0.5 smaller or less than or equal to negative 0.25? Well, that still might be tricky. So let's go ahead and draw a number line. And if I start with 0 here, and I want to go to -1 here, then negative 0.5 would be the halfway point. And that means that, negative 0.75 should be here, and negative 0.25 should be there. So the two numbers that we're comparing are this one and this one. The smaller one should be on the left. So that means that negative 0.5 is less than negative 0.25 since it is to the left of negative 0.25. Does that make sense? So that means that this is a true statement. So I'll just write true here. Does anybody have any questions about that one? Okay, so just to recap or reiterate, if you're given two fractions that you need to compare their values to see which one's bigger, you should probably use long division or your calculator to calculate what is their decimal representation. Draw a number line and then look to see which one is on the left. That will be the smaller value. Okay, so why did we do all of that? Well, we were trying to clarify, how do these inequalities work? Because we have to understand something about the number line and something about what gives value to these numbers. And so we need to introduce a concept called absolute value to help bring all of that stuff together. Okay. Absolute value is the distance a number is from 0 on the number line. Absolute value is represented by vertical bars with some number inside of it. So you would read this as the absolute value of X, whatever that number is. Okay, so you can think about this as like when you see a problem and you see a number that's enclosed in these straight vertical bars, that it's asking you, what is the distance that this number inside is from 0? Okay. So if I were to ask you, what is the absolute value of 7? Then I would write it like 7 with these vertical bars is equal to question. To answer this question, and it might seem really straightforward, you just need to know where 0 is on the number line. And then you count how many units does it take for us to get to 7 on the number line. So I'm going to count 1, 2, 3, 4, 5, 6, 7. And I counted a distance from 0 of 7 units. That means that the absolute value of 7 is just 7. Okay. But if I asked you, what is the absolute value of -3, that question would look more like this. The absolute value of 3 and -3 is equal to what? Now, can anybody tell me what is the distance that -3 lies on the number line from 0?
-3 units to the left of 0.
We got to be very careful here. So one thing that I should note is that absolute value is a lot like measuring something with a measuring tape. Okay, I just happen to have this measuring tape on me. If I were to measure, like go outside and measure a 2x4, and I needed to mark off 3 from one side, right? Maybe 3 feet. Then I would pull my measuring tape out, go out to 3 feet, and read on my measuring tape where the 3 feet mark is, which is kind of long out here. Okay. But if I were to turn around and measure the opposite side of that 2x4, I would still grab my measuring tape, go out to 3, and on my measuring tape, did the numbers magically turn to negative values? Well, no. When we measure distances, we only refer to them as positive distances. So the absolute value in terms of the distance that it's returning is just a positive number. So we can note to ourselves, like make a mental note, if we went 3 units to the right or 3 units to the left of 0, but absolute value is not concerned with the direction or the sign of the values. It just wants to know what is that distance. Okay, so distances are only measured in positive values. Okay, so if I was to measure the distance from 0 to 3, I want to clear this distance here to get us to -3. But really, I would just count the spaces that we skipped over. So 1, 2, 3, and I would say that there are 3 units here. So the absolute value of -3, again, is just telling me what is the positive distance from 0. And that is just 3. Does that make sense?
Okay, so I have a question. So
Yeah.
if it's -17, it'll just be 17.
Yeah, if I asked you for what is the absolute value of -17, then you have to think about it like, what is the distance that -17 is from 0? It's 17 units.
So practically just ignore the negative sign for the most part.
For the most part.
Okay.
Okay. Let's do some example problems just so we get used to it. Let's practice. And here's the idea, really. It's that the size of the number, you can think about the size of the number without thinking about its sign, right? Whether it's negative or positive. And that's like when we looked at, -5 versus -125. -125 looks like a bigger number. Its size looks like it's bigger. but it's actually a lesser value. Now, if we were talking about the absolute value of negative 125, that's what we're talking about, like the size or the distance from 0. But let's go ahead and say simplify the absolute value of each expression. Okay. So can anybody tell me what the absolute value of 6.3 is? Let me go ahead and see if I can make that sharper. There we go. Does anybody know what the absolute value of 6.3 is? What is its distance from 0?
Is it just 6.3?
That's exactly right. Right. So when it comes to positive values, you don't have to really worry about anything. We're just going to grab our number line if we wanted to. 0 is here. 6.3 is probably somewhere over here. But if I had to count or measure what is the distance here, it's 6.3 units. That's the distance from 0. That's what gives 6.3 its value. Okay. Let's look at another example. What is the absolute value of negative 5.1?
It's still 5.1, right?
Yeah, so if I go over here and walk to negative 5.1 on the number line, I know that I've walked in the left direction, but if I was just concerned with how many steps I had to take to get there, not the direction, well, I know that I've moved 5.1 units at some point, right? In some direction. 5.1 units is the distance that I've traveled. So that should be the answer here. The absolute value of negative 5.1 is just 5.1. Okay, let's do another one. C. What is the absolute value of negative 125? How many units would I have to walk away from 0 to get to 125?
125.
Yeah, 125. Does this seem like deceptively simple? Or are you guys a little bit, is it becoming a little bit clearer?
Yeah, I get it now. I just had to make
Okay.
sure. The negative sign.
Yeah. So you can think about it like this. The absolute value is like a machine that's just asking you, like, return what the distance from 0 is. Or in other words, if it's a positive, just spit out that positive number. If it's a negative, just spit out the positive number. So it's always asking you to spit out that positive number. Okay. Now, the one thing that might complicate the situation is if you have a problem that looks like this. Negative absolute value of negative 2.9. Okay. Because here you have to, and we haven't gotten to our discussion of order of operations and PEMDAS yet, but you might remember something from previous math classes. PEMDAS is just the order in which we have to do operations. And you might vaguely remember that we have to start with parentheses. Well, it turns out that absolute value is sort of like parentheses.
I've been having a lot of struggles with pandas.
Yeah, and we'll get to that in a later section and actually like double down on PEMDAS and really clarify it, hopefully. But for now, we need to treat absolute value sort of like parentheses, and we'll start by evaluating the absolute value first, and then worry about this negative sign on the outside later. So for a problem that looks like this, where we have negative absolute value of a negative number, just cover that outside negative sign up. And can somebody tell me what the absolute value of negative 2.9 is?
Positive.
Yes, it's positive 2.9. But because we still have this negative sign on the outside, we just have to keep it. And so that will be the answer. So that's the only part that might complicate it, is if you have a negative sign on the outside, then you might have a negative answer. But as far as absolute value by itself goes, the absolute value of anything on the inside will just be the positive version of whatever's on the inside. If it's already positive, it stays positive. If it's negative, you return the positive. Okay. Another type of question that you're going to see in your homework looks more like this. If the absolute value of x is equal to negative, let's say no, it's equal to 7, what are the possible values of x? Okay, so let's think about that for a second. This is asking us, if we have some number that has a distance of 7 units from 0, what are those possible numbers that have that distance of 7 from 0? What does x have to be? Is that a sort of confusing question?
Is it 7?
Yeah, x could be equal to 7 for sure. Is there another number on the number line that's 7 units from 0?
-7.
Yeah, or x could be equal to -7. So there are two values of x here, because if we think about our number line, and if we walk, this is our distance that they've told us. If we walk 7 units over here, what number do we land on? We land on the number 7. But if we start at 0 and walk in the left direction 7 units, what is the number that we land on? -7. So we have two possible answers here, two possibilities for what x could be. If they ask you if, let's say, y is equal to 0, what are possible values of y? What would the answer to this question be?
Still 0.
Yeah, x could only be 0, because again, they've given us a distance of 0. So if we're not any distance away from 0, we are at 0. So there's only one possibility here. And then finally, if they say, if z, some other number, is -3, if the absolute value of z is -3, what are possible values of z? Any ideas?
It's still 3.
Well, be careful here. We have to think about this. This is saying that if we have some number and its absolute value is -3, the absolute value of this number is negative. But we don't measure distances in negatives. Distances can only be positives. Well, we would say that this problem has no solution, since distances cannot be negative. So you have to be really careful. They might try to trick you up with a problem like that. Okay. But it's 12 o'clock. That concludes section 8.1. So when you have time, make sure that you get into the homework system and only work on section 8.1, right? That's all we've covered. And just get in there and see if anything gives you some challenges, if you're able to get through it. And if you have any questions, bring those to class next time, okay? If you have any questions and want to hang back and chat with me, you're more than welcome to do that. But otherwise, I will see you guys next time, same place.